So in this video, we will create an lwIP based application using the inbuilt Ethernet MAC of STM32 microcontroller. So some STM32 microcontroller like this one, this is STM32F439, and these types of microcontroller, they have inbuilt Ethernet support, and they have inbuilt Ethernet MAC, and after that we have a Ethernet PHY over here, and this is the Ethernet transformer, and finally we have this RJ45 connector where I have connected the Ethernet LAN cable. So these board, they have inbuilt 100 Mbps Ethernet connection, and now we will develop an application for this board. Previously we were developing application for external this Ethernet controller like ENC28J60, but this time we will use the inbuilt Ethernet of STM32 microcontroller. So now let us see how to do this. And the easiest way to get started using this method is using these Nucleo boards, because these Nucleo board, they have the complete support for this 100 Mbps Ethernet. That means they already have this Ethernet PHY chip, they have the Ethernet transformer, the RJ45 connector, so everything is ready. So we can easily get started developing our application using the lwIP stack on this platform. So I suggest you to purchase one of these board, and this Nucleo board, it is STM32F439 based. So there are two versions, STM32F429 and one is STM32F439. So the latter one, that is 39, it has the crypto engine inbuilt. By crypto engine I means the engine that is used for data encryption and decryption, and that is useful for when we use an encrypted connection like HTTPS. So I have so it is better to choose the latter one, that is the STM32F439 base. So please order one of these board and get started. So start your STM32 Cube ID and start a new project. Enter the part number of the microcontroller. It is STM32F439ZI. So this is the microcontroller. So here it is, the microcontroller. Select this one and select next. And here we have to enter the project's file name. Just enter a project name like this. These option will be something like this. Hit next and finally hit finish. It will create a new project for us. So you will get this view, and this is for the STM32 Cube. So this is the STM32 Cube GUI configurator, and we will start configuring our project from here. The first thing that we need to do is to go inside this system core section, and here we have to configure the RCC, and this RCC stands for the reset and clock controller. And first we have to select the high speed clock source. By default it is disabled, but here we have to select this option, that is bypass clock source. And why we are selecting this option, I will discuss. And second thing, this is the low speed clock. This one is used for the RTC or the real time clock. We will also enable this because we have this crystal oscillator soldered on the board. Now let us select crystal ceramic resonator here. Just a moment. So here in this project we are using this Nucleo board. This is STM32F439 Nucleo board. So we have to open the user guide of this board, and here I have that user guide or the user manual. This is very important document, and the ID of this document is UM1974. So you can search this manual on the ST's website, and after downloading this we can go through this. So now I will tell you why I have selected bypass clock source here and not crystal ceramic resonator. The reason is that this board, this Nucleo board, so this board, it does not come with this external oscillator, main oscillator. The space is there in the PCB. Here you can see the space is there for X3, but no actual part is soldered here. And also this solder, this SBs, this stand for solder bridge. So solder bridge, these two solder bridges are not sorted, so this microcontroller is not connected to this crystal oscillator. And also these two load capacitors, that is the C38 and C37, they are also not populated in the PCB. But as you can see, this low speed oscillator which works for this RTC, it is soldered there by default, but this one is not soldered there. So we cannot use external oscillator with this board. If you want to use this external oscillator, you have to solder these parts manually here by yourself. But currently we are not using this. So how this microcontroller is getting the clock? So this microcontroller is actually getting its clock pulses from the top section here, the ST-Link section. This one, this ST-Link is providing the clock source through the MCO pin. So this microcontroller, it is providing a single clock pulse to this microcontroller, our main microcontroller. And to use this kind of clock pulse, this is actual clock pulse and not a crystal oscillator. This is means proper electrical signal, the clock signal, it is coming from this microcontroller to this microcontroller, and we are not using this crystal oscillator. That is why we are using bypass mode here. And one thing you have to note, that this ST-Link, this provide a fixed 8 megahertz clock source to this microcontroller. So this microcontroller is providing 8 megahertz clock signal to this main microcontroller. So while configuring the this clock, when we will go to the clock configuration section here, we will enter 8 here, because we are getting 8 megahertz from the ST-Link part. Now let us move on to the next configuration, and this time we will go to the SYS or the system section like this. So by default this debug is disabled, we have to enable it. And here we have to select this, not the JTAG interface, we have to select the serial wire interface, because our development board is using serial wire for debugging. And one more important thing here we have to do, we have to change the timer which is used for the time based source. And here we have to, I will select this timer 6 here. You can also select timer 7. So this timer 6 and timer 7, they are the basic timers. That means they don't have these output compare, PWM, those kind of features. So these are the simplest timer. And the time based source, we can use simplest timer. We do not have to waste one of these advanced timers. That is why we will choose either timer 6 or timer 7. And you can learn about these timers from the data sheet of this microcontroller. So let me open the data sheet. So here I have the data sheet of my microcontroller, that is STM32F429. So here I have to go to this section, functional overview, and then I have to go to the timer and watchdog section, where it is watchdogs and timer, or timers and watchdogs. So here it is, timers and watchdogs. So here if we compare the features of various timer that is available on the microcontroller, we have to go to this section, that is timer feature comparison. So here they compare, they have given a whole table, it is table 6. So here you can see on this table that we have advanced control timer, these are the most expensive kind of timers, and it is timer 1 and timer 8, they have most features available. And then comes the general purpose timers, they comes after this advanced control timers, so they also have lots of features. But finally we have this basic timer, these have the least number of features available, so these are the most simple timers. So it is better to first use these timers for this simple application, and if we do like this, then all these good timers, these feature rich timers, they will be available for our later use for some other advanced application. That is why I have chosen timer 6 or timer 7 for this time based application of this HAL layer of the cube ID. So where is timer 6? Here it is. So now these HAL libraries, the ST's HAL or the hardware abstraction library, they will use timer 6 for simple this time based source. That means for the delay purpose we use functions like HAL delay. So it will use this timer for this calculations for the timekeeping purposes. Now what is the reason that we are changing the default timer here? By default it was Systic and we have changed this to TIM6. So why we have done this? Why we have done this? So the main reason is that this project is going to be a free RTOS based project. So this project will not be a bare metal project, but it will be running over an operating system, a real time operating system that is free RTOS. And this free RTOS also needs a clock source for its main scheduler or this for preemptive multitasking. It requires a timer. And generally the best timer to use with free RTOS is this Systic timer. So we are using this Systic for our, that is tick source for our free RTOS real time operating system. That is why we are using TIM6 here for HAL libraries. Now let us configure the clock. So go to this clock configuration section, and here we have already entered 8 because we are receiving 8 megahertz signal from the ST-Link MCO. And here we have to change this clock source for our PLL. By default it is coming from the HSI or the high speed internal clock source, but we will switch this to HSE or the high speed external clock source. So now we are receiving 8 megahertz to the input of our PLL. This is the main PLL, and then we have here we have to divide this clock source by 4 actually. So in this way here at this point we will get a 2 megahertz signal, and we will multiply it by 180. Here, and finally we will switch this main clock. This is system clock mux or the multiplexer. So this is the system clock. Currently by default it is getting a direct signal from the HSI or the high speed internal. We will switch it to the PLL for high frequency operations. So you will get, we are getting 180 megahertz here, and this is also the maximum clock speed that this microcontroller supports. So our H clock, it is 180 megahertz, but here we have some problems. That is our two of our peripheral clocks, that is peak clock 1 and peak clock 2, they are getting overclocked. So the maximum this our first peripheral bus, that is peak clock 1, it supports, here it is written that it can go maximum only up to 45 megahertz. So here we have to divide this by 4. So now we are getting good 45 megahertz here. So this is the slower peripheral bus, and all the slower peripherals are connected to this bus. This is APB1 or the advanced peripheral bus 1. And next we have a better peripheral bus, and to this peripheral bus all the high speed peripherals are connected, and the maximum clock frequency of this peripheral bus is 90 megahertz. So this time we have to divide this by 2. In this way we have properly configured our clock source. Now let us save the project by going to the file and save all option. Now moving on to the next item, we will go to this connectivity section. Here we will enable our this UART3, this one. So we will use this for debugging purposes. We will use printf style debugging, where we will print messages to show the progress going inside the microcontroller, and we will use a terminal program to view those messages on our PC screen. So here we have to select USART3, and we have to use the asynchronous mode. It will enable the UART, but we have to change the pin configuration. So by default, this STM32 cube ID, it selects these GPIO for UART3. So here we can see clearly that our PB10 is UART-TX and PB11 is UART-RX. But now we have to consult the schematic of our development board to see where these are connected. So now let us open the schematic of our development board. So here I have the schematic of my development board, that is the Nucleo development board. And now let us see, analyze this schematic. Where is the UART lines? So here we have, so as we can see, this is our microcontroller, that is U8B, and here they have used PD8 and PD9. So here PD8 is the UART-TX and PD9 is the UART-RX. And here is the connection coming from our ST-Link part, the top portion of our development board. So it is going there. So the TX of our microcontroller is going to the RX of ST-Link, and this RX, that is the receive pin, is connected to the TX of ST-Link. So we have to configure something like this, that is we have to make PD8 as the UART3 TX. So let us note it down somewhere and then do the same modification there. So now let us go back to the IDE and find the pin PD8 and PD9. So here they are, PD8. So we have to make this pin PD8 as the UART-TX pin. So here we can see the alternate option, that is UART3 TX. When we click this, this will go there, jump there. See, this has gone here. Similarly, change this PD9 to the UART RX pin, that is the UART3 RX pin. Now we have properly configured the UART. Now let us configure the main peripheral, that is the Ethernet. It will also be found inside this connectivity section, ETH. So here we have to enable our ETH. So the ETH MAC, the ETH peripheral of our STM32, it supports two connectivity mode. So the first one is the MMI, or the standard mode. So this MII, this stands for medium independent interface. You can search this on Google also. So this interface is used to connect the output of MAC layer to the file layer, actual file layer, the physical layer. So there are two modes available. One is the MII mode, or the medium independence mode, or reduced medium independent interface mode. So this one is used inside bigger motherboards, bigger processor, like in our PCs or laptop. And there is the alternate version, that is this reduced version, and this is mostly used inside embedded systems. So these use less so this mode, that is the RMII mode, this use less number of GPIO pins. That is why this is more suited to embedded applications, small applications, compact applications. That is, but our STM32, it supports both modes, so you are free to connect both types of Ethernet MAC to this chip, our STM32 chip. But in our current development board, they have used a PHY chip which uses this connectivity option, that is RMII mode. And you can get the details from the datasheet or the user manual of our development board. So now let us open that. So now let us select RMII here. And as you can see that the IDE has enabled some of the pins here, and these pins will be connected to the PHY chip. So now let us zoom to this area. I will reduce the size of this pin, something like this, or I will minimize this using this button. So I have minimized this. So here at the bottom area we can see the pins, the Ethernet pins. So what are the pin? Here we can see that they are prefixed with this thing, that is ETH. So the first pin is ETH MDC, ETH reference clock, ETH MDIO, ETH CRSTV, ETH RxD0, ETH RxD1, ETH TX enable, TXEN, and Ethernet this TXD0 and TXD1 pin. So these are the pins that will be connected to the PHY chip. So here we can see the development board, and here is our main IC, the main microcontroller, or the STM32F439. And below this main microcontroller, here we have the Ethernet PHY area. So this one is the PHY chip, and this PHY chip is connected to the main microcontroller using the RMII interface. And here we can see the zoomed image of this PHY chip, and from here we can read the part number, that is 8742A. So if you search this in Google, you will get the data sheet just like this. So this one is the chip 8742A. So this chip is currently produced by the company called Microchip. This company is popular for producing the PIC series of microcontrollers. But actually here you will notice that there is no microchip branding here, but you will see the branding as a SMSC. So this is actually the company, this was the company which was producing this chip, and Microchip acquired this company, that is SMSC company. So this was a smaller company. Microchip purchased this company entirely. In the same way, they have purchased Atmel also. The Atmel company is popular for producing the AVR or the 80 mega series of microcontroller, which is also used in Arduino boards. Now I will go to the schematic of the development board here, and I will open the Ethernet section like this. So here on the extreme left, we have the signals coming from the microcontroller. These are the signals coming from the PHY output of the microcontroller. And here we have our PHY chip, that is the LAN8742A. This is the same chip, this chip 8742. And here in the schematic we can see that it is U9, and here also you can see that it is labeled U9. So this is the chip, and the output of this PHY is going to the, this first it is going to this Ethernet transformer. This is U11, this is the Ethernet transformer. We can see this here, this one. Let me zoom here. This one is the Ethernet transformer, actual Ethernet transformer. So if I zoom here, you can see the part number also, KMS1110, and this one is U11. And let us go back to the schematic. This is KMS1110 and this is U11. And finally the output of this transformer is going to this CN14, and this CN14 is the actual RJ45 connector which is used to connect to the Ethernet. And here we can see the designator, it is CN14. And if we go to the, here you can see that this is CN14 here. So this is the RJ45. Here we plug our LAN cable like this. So what we have to do here, we have to make a list of all these pins that is used for interfacing this PHY area. So let us begin. I will open a Word document like this, and I will create table here, and I will here I will feed the name of all the signals used. Okay, so I am feeding this name of these signals. So let me open this side by side. Let me try to open this side by side. Perfect. So the first signal is this TX enable. I have TX enable here. Then I have TXD0, TXD0. In the same way TXD1, TXD1. Then RxD0, RxD0. RxD1. Here we have RxD1. Then this CRS div, this CRS div. Then MDC and MDIO. So MDC and MDIO both are present here. And then I have the reference clock also. It is here, the reference clock also. Now the second thing what we have to do, we have to get the mapping to the MCU port. So it is also written here in the schematic. So in the second column of this table I will put these things. like this TX enable signal, it is actually available on the PG11 pin of the microcontroller. So this PG stands for port G pin 11 or bit 11. So I have put that in the table here. In the same way, PG13, 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 PB13, then PB13, PC4 and PC5, PC4 and PC5, then PS7, PS7, PC1, PC1, PA2, PA2, PA1 and PA1 finally, like this. And now the third thing that we have to do is to go to the cube ID and then match whether the pins that have been assigned by the ID is correct or not, means it is matching our current hardware or not. So you have to go to this, then you have to open these two things side by side. From here you have to match it. Like here we can see that the Ethernet reference clock is on PA11. So let us go to our document and see that this one is like it is reference clock, it is on PA1. So here we can see in the cube ID that Ethernet reference clock is on PA1. In our document it is also in PA1. So I will write checked OK here. In the same way I will check the other signals. So if you go on checking the signal, you will find that two signals are not matching. Two signals are not matching here. So now let us see where is the mismatch. So mismatch is in these two pins, that is TXEN. So now let us see where it is TXEN. So TXEN is here on PB11. But on our table if we see that our TX enable should be on PG11. So let us change this PG11. Okay, so where is PG11? So PG11 is here, but currently our cube ID, it has assigned this TX enable here on PB11. So this will not work in our board because in our actual hardware connection it is on PG11. So here we have to assign this signal, that is Ethernet TX enable. Done. See, in the same way we have to change this second mismatch also, that is we have to change the position of this TXD0 to PG13. So where is our TXD0? TXD0 is here on PB12. It won't work. It should be on where? It should be on PG13. Where is PG13? Here is PG13. TXD0 we have to assign here like this. Now it is fully compatible with our hardware.